Hello, so today I'm going to be explaining chapter 10, like some exercises from chapter 10 on the chemistry textbook. So this is the fifth time I record this because it never saves, so this is the last time I'm going to record it. And I'm done because I've been explaining this for so long. It's been like an hour. So in each of the following groups of substances, pick the one that has the given property. Justify your answer. So highest boiling point. So there are three forces: LDF, bonding dispersion, then it's dipole, and then hydrogen bonding. So it's essential for you to draw like the substances. Okay, then you have HBr, the molecular geometry. Then so Cl is diatomic. Diatomic are non-polar, meaning they're symmetric. So they don't have dipole. Dipole is for polar molecules. Or hydrogen bonding is not like hydrogen bonding with hydrogen, or like no, it's not that. It means like a hydrogen with an oxygen, hydrogen with a nitrogen, or hydrogen with a fluorine. And LDF is related to the molecular size. So the bigger the molecular size, the bigger the LDF. Okay, so and the smallest molecular size is the weakest LDF. So now we have these three. Highest boiling point. Highest boiling point is related to, so like it's directly related to intermolecular forces. So meaning that the higher the stronger the intermolecular forces, the higher is the boiling point. So which one has the strongest intermolecular forces? So every single thing has LDF, bond dispersion. So okay, so this one is polar. So it has dipole. It doesn't have hydrogen bonding. None of them have hydrogen bonding. Each one of them has LDF for sure. LDF. And then this one doesn't have a dipole moment, so it's gonna be HBr. Okay. I want to make sure this is recording because like I'm so tired of this. Oh my god, it's almost 2 a.m. Okay, next question. So its highest freezing point. Okay, highest freezing point. It's also related to the intermolecular forces, so the stronger the molecular forces. Intermolecular forces is gonna be the one. Okay? So now we have H2O. Then NaCO, then HF. So all of them have LDF. So we all know that water is polar. So dipole, and then hydrogen bonding. This one has hydrogen bonding. This one has dipole, and hydrogen bonding. Dipole, hydrogen bonding. This was dipole, but doesn't have hydrogen bonding. The difference between the three is that actually the NaCl it's like strong ionic, like the attraction between the Na and the Cl is stronger than like the water or like a HF. So it's gonna be NaCl. So then lowest vapor pressure at 25 degrees C between Cl2, Br2, and I2. So all of them are diatomic, so they're all gonna be non-polar. So that's discarded. None of them has like hydrogen bonding, so it's gonna be up to the LDF, meaning the molecular weight. So now what are you gonna do? You're gonna go on your periodic table and you're gonna add the molecular weights of the compound. So Cl is like 35.45, then you add 35.45. It's gonna that. So as you can see, like on your periodic table, iodine has 126, so it's the one that with the highest. So 126 plus 126 is gonna be like 200 something. So it's definitely this diatomic. Oh, also I forgot to explain that lowest vapor pressure is not going to be like the highest freezing point, like it's directly related to intermolecular forces. It's actually inversely related, meaning that the higher the intermolecular forces, the lowest the vapor pressure. So that's why it's this one. Sorry, I forgot to mention that, but that is really essential to know. And then, God, lowest freezing point. So the lowest freezing point is going to be the one with the weakest intermolecular forces, right? So then you have N, and then you have CO, and then you have C. Okay. So each one of them has LDF. This one is non-polar. Non-polar, and doesn't even have hydrogen bonding. None of them have hydrogen bonding. But this one has dipole-dipole. And this one's non-polar. Oh my god. So between the three, so this one is out, okay? So between nitrogen N2 and CO2 is gonna be N2 because it's like the smallest compound present. Like the smallest like non-polar, because if you add the molecular weight of CO2, so like 12 plus 16 is gonna be like 40 something, right? And then N is gonna be like 28, so it's gonna be N2. Lowest boiling point. So all of them are higher carbons, so all of them are non-polar, they're symmetric. How do you know the lowest boiling point? As I mentioned before, the intermolecular forces. So the weakest is LD forces. The weakest LD forces because they don't have like hydrogen bonding or they don't have dipole-dipole. So the weakest LD forces is gonna be the one. Okay, so I feel like it's pretty straightforward. Like CH4, like this definitely has like CH3 or CH3 CH2 has definitely like a bigger molecular weight. So CH4 has the smallest molecular weight present. So it's gonna have the lowest boiling point. So then highest boiling point is gonna be the one with the more intermolecular forces. Okay. So now let's see this. HF, HCl, oh my god, HCl, and then HBr. So this one has dipole-dipole, dipole-dipole, dipole-dipole. This one has hydrogen bonding. All of them have LDF. So it's definitely HF. Okay. Hydrogen bonding is literally the strongest thermonuclear force between the three. Like it goes from hydrogen bonding, then it's dipole-dipole, and then it's LDF. So now the last one. Lowest vapor pressure. Okay, at 25 degrees C. CH3, CH2, CH3, okay? So it's essential to draw to like the Lewis structure, okay? So it's gonna be easier for you. So then you have C, 3 carbons, and you go like this, and you start adding everything. So H, the carbons are connected, and then, right, that is non-polar. has this, like, hydrocarbons are non-polar. I mentioned that before, okay? So, lowest vapor pressure. I don't believe this one. Like, so far, I don't believe this one is the one. So then you have C, H3, H, 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 and C, and then you have oxygen connected. Have C, C, H, 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 right? It has. Let me see. It doesn't have hydrogen bonding though. It has dipole because it's non-polar. It's polar. I mean, symmetric. Asymmetric. Okay. So it has LDF. This one also has LDF, but this one I don't feel like it is. Like, so far, this is not it. So then you got CH. C, C, H, 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 C, H, H. Oh my god, this is bad. H, H, and then OH. So, this is polar. Okay. It's dipole, and also has hydrogen bonding, so it's gonna be this one. It has the hydrogen bonding. So it's like this one. The HF has a hydrogen bonding. It's okay. This is so far for the first question. So, okay, now for the second question is, I don't know how to pronounce it. I don't know how to pronounce that. In Brokerage, I don't know. Colorado, the typical atmospheric pressure is 520 torr. What is the boiling point of water? Big. Okay, 40.7 kilojoules. Well, okay, so they're saying they want to know the boiling point at 520 torr. Okay, so we already know that water regularly, like in standard conditions, is 100 degrees C, and then at 1 atm. So then, which is essentially 760 torr. So at 120 torr, how many degrees C? Okay. It's gonna be like everything. So since they're giving us this, so they're giving us pressure, I believe we will have to use this equation. So we're gonna be looking for T1. So it's like that temperature with associated with the 520 torr. So P1 is gonna be 520 torr. P2 is gonna be 760 torr. And T2 is gonna be 100 degrees C, but since we're gonna use our R value, that is, what is it? It's 8.314 kPa L. Okay, so this essentially this is joules. So you need to use this R value in order to like cancel the heat the heat unit, right? So this is joules though. So we need to change this to joules, which is gonna be 40.7 divided by multiply by 1,000, so it's gonna be 40 joules. Okay. So I think we have everything. Oh, we also need to like change the equation. So we're gonna have to pass this like multiplying, and then this one dividing, and then the other one. Okay, so it will look like this. T1, P1, P2, then R, right? Yeah, and then plus 1, 2, 2. And now we plug all the numbers. 520 torr, 760 torr, 5 kPa 1K, then it's 40 mole, and then wait, I think I forgot. Okay, so you need to change this Celsius to Kelvin. So you're gonna go 100 plus 273.15, and it's gonna give you the Kelvin. So it's gonna be 373.15 Kelvin. 373.15 Kelvin. This cancels. Cancel. Okay. Wait, actually, you don't cancel the Kelvin. Also, you're dealing with temperature. You need that unit. Oopsies. Okay. So now you plug that in the calculator. Don't forget the negative. Oh my god. So you're gonna get this. Oh no, bro. Oh my god, I did, look, I put multiplying here, but it's actually just, adding. Oh my god, I have to redo this. Okay, so don't make the same mistake I did, so it's actually plus, okay? So now you're gonna get 2.757. So, but we actually need T1, so now we're gonna like to the power of -1, so it's flipped. That's an algebra rule. So now this like 362.65 Kelvin. But I think they want it in degrees Celsius, so it's also, if you want it in Celsius, you're gonna go to 73 minus 15.15, sorry. You get 89.50 something. So this will be the answer. I think it's pretty like good problem, I guess. Okay, so next problem. What quantity of energy does it take to convert 0.500 kilograms of ice at -20 Celsius to steam at 250 degrees Celsius? Specific heat capacity is ice 2.03 joules per gram Celsius. Liquid 4.18 joules gram Celsius. Steam 2.02 joules gram Celsius. And then what is that? Oh, so it's H. For vaporization, it's gonna be 4.7 kilojoules of mole per mole, and then fusion is 0.02 kilojoules of mole. Okay. So for me, what it helps is like, like I need to visualize this. Okay. Oh, that's ugly. Yep. So it's saying that it starts at negative 20.0. So it's water, so it's gonna be ice at that point. So then the freezing point is 0. Then the boiling point is gonna be 100. Whoops. What is it? Because it's in a system, right? Like 250.0. Okay. So it starts as ice, so it's a solid. So then there's gonna be heat. Oh, this is heat and this is temperature. And this is okay. Okay, so it's gonna go to 0. And now it's gonna be solid. But there's gonna be a phase change to liquid. Period. So then it's gonna be heat again. Like energy. Energy, okay, sorry. Okay, Q. So then, oh my god, I got lost. So then, this is still liquid. Now it's gonna be a phase change again of gas. Now it's gas, and now it's gonna be a temperature change to that. So then it's Q1, Q2, Q3, Q4, and Q5. In order to know that here in this case, in this graph, Q1, Q3, and Q5 are temperature change, and then phase change are gonna be Q2 and Q4. That is important to know because they have different equations, okay? Okay. So for temperature change is gonna be for temperature change it's gonna be so the M yeah. So it should be MC delta T. Oh, sorry, Q. This is for temperature change. So the mass, we have the mass, but as you can see, the C that they give us is as grams. So we need to change that. Okay. So 1 kilogram is equal to grams, and then 0.5 kilograms. That's gonna be 500 grams. Okay. So Q1 is gonna be equal to 5 grams. Since solid ice. All the solids is going to be 2.03 joules grams. So delta T. What is delta T? Delta T is T2 minus T1. I'm so sorry, that is not what I meant. So TF, T1. So T final is minus T initial. So the T final here is going to be 0 though. But the T initial negative 20, so it's going to be. But it's going to turn positive since the negative changes the sign. So it's going to be positive 20. So be aware when you put that in your calculator. So now we're going to do that, multiply, and let's see what we get. Well, I got joules, okay? So I forgot to put these here. But yeah, sorry. Okay, so there. So now we're gonna do Q2. Q2 is a different equation because it's phase change, okay? And for phase change, in this case, since, let's see, it's kilojoules per mole. Oh, so it's mole. So now we're gonna do this. This is gonna be the equation that we're gonna be using, okay? So we need the moles of this. So how do you calculate that? You need the molecular weight. What's the molecular weight of water? It's 18.02 grams per mole. It's gonna cancel out, and then you're gonna get, let me see, 500 divided by 18.02. You're gonna get 27.746, but it's around to 275. It's gonna be that, okay? So 27.75 mole. So it's solid to liquid. What is solid to liquid? That is fusion. So you're gonna multiply by 6.02 kilojoules mole, right? Is that right? Yeah. Let's cancel. You're gonna get kilojoules. 27.75. So it's 167.055, right? But we want that in joules because I'm gonna do joules. Okay. Q2 and Q3 is gonna be the same one as Q1. So 500 grams of, but of course the C changes, okay? The C changes because now it's like liquid. So for liquid it's 4, oh my god, 4.18 joules grams. And then the delta T. What's the delta T? It's the T initial is 0 and then that one is 100. So it's joules. 500, 4.18. Okay. 20. Okay. I think joules. We're doing joules, right? Okay. So then now Q4 is gonna be the same one as Q2, and or the moles. The moles are 27.75. 75 mole. The fission, and now it's like vaporization, so it's gonna be 40.7 joules mole. And it's 27.75. So now we only have one left, which is Q5. And it's the same one as Q1, 3. So, the grams. But of course the C changes because now it's steam, so it's 2.02. 2.02 joules. And also the delta changes, of course, delta T. So now it's from 100 Celsius to 250, right? Yeah. So now we put that in the calculator. Okay, joules. So Q total. It's gonna be Q1 plus Q2 plus Q3 plus Q4 plus Q5. That's why it's important to like put in the same what is that? The same units. So you're gonna go 20 joules plus 167.055 joules plus 20 joules plus joules plus joules. So that's gonna be equal to oh wait, no, wait. I'm adding this wrong. I forgot to add a number. I mean, I don't know. I got joules. So then that in kilojoules is gonna be I think this is pretty much it. I don't think we have to answer anything else in this question. So yeah. So this is the last question for the night. Okay, it's 2 a.m., but we're gonna finish strong, okay? So use a companion pace diagram for carbon. Is it carbon? Yeah, it's carbon. To answer the following questions. So it's the first question is how many triple points in the phase diagram. So triple points is like this triple points, 3. When like the 3 pieces can concede, is it? Points concede? You know what I'm saying? Like they intercept. That's the word. Yeah. Triple points. So there are 2. What phases can coexist at each triple point? So there's 2. So okay, the red one. It's gonna be as the red one. You can see this one, this one, this one. So diamond, liquid, and graphite. I don't know how to pronounce that. So then is vapor, liquid, and yeah. So like at the highest pressure is gonna be diamond, liquid, graphite, and at the lowest one, which is this one, lowest pressure, vapor, liquid, and graphite. Okay. So what happens if graphite is subjected to very high pressures at room temperature? So very high pressures at room temperature. Room temperature will be around here. Actually, like, yeah, here. So wait, no. Well, yeah, we'll be like around here. So then high pressure. It's gonna be diamond. It's gonna convert to diamond. So yeah, like you gotta look at the graph. I don't know, like very high pressures. You firstly have to like understand your x-axis and your y-axis. If you don't understand that, then but like they're essentially telling you like room temperature temperature should be around here, you know, and then the pressure is telling you as the pressure increases, right, at room temperature, what does this like change to? Like what happens when that pressure increases? Well, it becomes diamond since this space is right here, right? So then if we assume that the density increases with an increase in pressure, so density increases as well as pressure, so they both increase. Which is more dense, graphite or diamond? So since pressure, so if pressure is high, then that means that the density increases as well. So it's gonna be more dense. So the higher the pressure, the more dense the thing. So it's gonna be diamond again. I mean, graphite, when it comes to higher pressures from the last question, it becomes more dense. It becomes like diamond. So yeah, it makes sense that diamond it would be the one that is like more dense. So I think, yeah, those are all the questions from this problem. And I hope this was helpful. You know, like at some point in the video I was kind of rushing or like, and I like repeated myself, but I think I corrected my errors. I mean, it's 2 a.m. in the morning and I had to redo this like 5 times, but hopefully this is the last time. So thank you so much. I hope this was helpful.